We're going to continue our notes on continuity. There are three types that we're going to look at. The first type is called our jump discontinuity, and this is where the left and the right sides don't match up. Here's an equation, f of x equals absolute value of x divided by x, that has this jump discontinuity. If we take a look at the graph, as x approaches 0 from the left, we can see that all of our y values are equal to -1. And then as x approaches 0 from the right, we can see that all of these y values are equaling +1. Now the discontinuity occurs when x is 0, and that of course is where our denominator would be undefined. You can't have 0 in your denominator. Otherwise, the function is continuous everywhere. So from -infinity to 0, jump over 0, so we'll use that union with the parentheses, and then from 0 to infinity. And I'll just make a little note, x can't be 0 in our denominator. The second type is our removable discontinuity, and this one sometimes doesn't even show up. But really what you've got is a little hole in your graph. So when we've got a rational function like this one, f of x equals x squared minus 2x over x minus 2, of course our first step is always to factor and simplify. In the numerator, our common factor is x. So if I factor that out, I'll be left with x minus 2. And we can see that in both the numerator and the denominator, we have this common factor. When we cancel that, what we have left is just f of x is equal to x, which is just this linear function. Our hole occurs at this common factor when we solve for it. And so we add 2 to both sides, and x is 2. That's where we have our discontinuity at an x value of 2. If I wanted to find the corresponding y value, I would substitute this 2 back into our function. So we'd have f of 2, and wherever we have an x, we just substitute in a 2. So we can see that at x equals 2, we have a y value of 2, and that's the coordinate where we'd have our hole. And so on our graph, it would look something just like this. Everywhere else, the function is continuous. And the last type of discontinuity, this is our infinite discontinuity. And this is where we have a vertical asymptote. We're looking at another rational function, and where the denominator is equal to 0, the function is undefined, and so that's where we have our vertical asymptote. So we set the denominator equal to 0 to solve. If we add 2 to the right side, we have our vertical asymptote at x equals 2. So that's going to happen right in here somewhere. Everywhere else, the function is defined. So how do the functions behave around the discontinuities? Well, if we're looking at the left side of behavior near a discontinuity at some value c, verbally it looks like it's read like this. As x approaches c from the left, and I'm going to go ahead and write it symbolically, c from the left, this little minus sign indicates from the left, the function value can approach or equal a constant, or it will approach a constant, or negative or positive infinity. So it just depends on what you're looking at. But f of x can have some options. It can equal a value, as this first problem did. So I'll just go ahead and write this up here. As x approaches 0 from the left, the function equaled -1. And as x approaches 0 from the right, the function equals +1. And so we have options. It can either approach or equal a value, or it will approach positive or negative infinity or a value. Just depends. All right, in the next, let me continue at the bottom. And then from the right, I didn't finish writing this, as x approaches some value from the right, the function can either approach or equal a value or positive or negative infinity. And so let's go ahead and write these for the next two problems. As x approached and we had the discontinuity at 2, Now this time the function approaches 2. It cannot equal 2 because that's the value that is undefined. And so we're just going to say it's approaching 2. And I'm going to say from the left, and then again from the right, the function is approaching 2. So you can't really see the discontinuity in this problem because these two are equal to the same. We did see that in the first problem where they equaled +1 and -1. That's an obvious discontinuity. Here, this is a little bit less obvious. And in the last problem, I'll go back to my blue, as x approached 2 from the left, the function, now you can never equal positive or negative infinity, so we're going to say it approaches negative infinity because if you were tracing this and you're getting closer and closer to 2, our y values are going down forever. That's negative infinity. And then from the right hand side, as x approaches 2 from the right, the function, again, can't equal, but it can approach positive infinity. And here's what it looks like from the right hand side. We're going to continue up forever. Okay, and I think we've got a couple last examples. For number 4, of course, you have your vertical asymptote, so that's your infinite discontinuity. And so as x approached 2 from the left, f of x is approaching negative infinity. And as x approaches 2 from the right, f of x approaches positive infinity. Seems very familiar to that last one. Guess I need to get a new example. All right, and then two last, we have one with jump discontinuity. And as x approaches a from the left, we're getting closer and closer to a. Our function, f of x, is, it looks like it's approaching. It's not going to equal because it's got an open circle. It approaches L. And as x approaches a from the right, the function is going to approach m. Again, it can't equal because you have that open circle. And the last one, this is our removable. And as x approaches -1 from the left, the function is going to approach 1. It's not going to equal 1 because, again, it's undefined there. And as x approaches -1 from the right, the function is going to approach